Hello friends, Uncle Lee here with you. It's a little explanation of the fundamental theorem of calculus. By no means, ladies and gentlemen, is this the proof of the fundamental theorem of calculus. I believe that's going to be a little bit out of the realm of Uncle Lee's. But it is certainly a nice explanation, a nice verification. It has been said that the fundamental theorem of calculus, by folks far more intelligent than I, that the development of the fundamental theorem of calculus is one of the greatest accomplishments of the human mind ever. That's a pretty big statement. So what I want to bring to you today, lay it down on the table, is a nice little explanation of both parts of the fundamental theorem of calculus. There's a few things that we need to know before we go there, and a few things that we do need. If you're at the point in your study of calculus that you're studying the fundamental theorem of calculus, then by golly, you know what a definite integral is. You know what an antiderivative is. And you certainly know what the formal definition of the derivative is. And those are three things that we're going to recall briefly before we get into that discussion of the fundamental theorem. The definite integral. The definite integral. First of all, it's a number, and we know that. And so if we're talking about the definite integral of f of x from x equals a to x equals b. And for the case of this discussion, we're going to keep f of x above the x-axis, i.e. we're going to let f of x always be positive. It's just going to make our discussion nicer, if you will, cleaner. And so I've got this integral from a to b of f of x dx. This is a number, and we all know what that represents. And in this case, since f of x is above the x-axis, this definite integral represents area. Okay, and we know about if f of x wanders here below the x, then it's net change and things of that nature. Right now, let's just talk about positive f of x. Okay? And then we've got this concept of an antiderivative that certainly we've discussed and that all good calculus students by this time know all about, right there. And so if we just take the antiderivative of f of x dx, that's going to be capital F of x. That's what we call it, capital F of x. And you put a little c on here if you want. That constant of integration, if you will, which is good if you're doing some differential equations. Not good, it's imperative. But this statement here is true. The antiderivative of f of x dx is equal to capital F of x if and only if the derivative capital F of x is equal to little f of x. That, by definition, is the antiderivative of little f of x. Capital F of x is an antiderivative of little f of x, by definition. Okay? And then the most fun fact, the formal definition of the derivative. And this is where we had all the fun. It's been a while since we talked about this. But what is f prime of x? F prime of x, we know, is the limit as h goes to 0 of the quotient f of x plus h minus f of x over h. All right, then. So let's talk about, then, f of x where f of x is greater than 0. I want to be that purple curve right there. And what we're going to do is we're going to create an area function of x. We're going to create an area function of x. I talked about that when I was speaking to the definite integral. And I'm just going to let this be a of x, and a of x is going to be the area under f of x from 0 to some x value. We can put that x value wherever we want. We can put it right there for right now, if you will. So, I created this area function. Later on we're going to call it an accumulation function, a net change function, if you will. But right now, just for the sake of understanding, we're just going to call it an area function of x. And that area function is going to be the integral from 0 to x f of x dx. And x is going to be our variable, our component of this function, our input of this function that changes. And what I want to do, using that area function, oh, let's see here, I think I just did that right there, same slide. What I'm going to do is I'm going to look at a yellow area. Same area function, same f of x above the x-axis, and I'm going to call that yellow area, and I'm going to let this b be an arbitrary x value. And so a of b, I'm going to find that to be the yellow area. That's simply going to be the integral from 0 to b of f of x dx. F of x dx. So a of b is the integral from 0 to b of f of x dx. Easy enough. Area function, accumulation. All right? And then I want to look at some green area right there. And I want to go to a. It's a little a. And a is also another x value. And the green area this time is going to be, we're going to define it to be a of a, using that area function. It's going to be the integral from 0 to a, f of x dx, is the green area. What I'd like to consider now is that yellow area, subtract from it the green area. So I want to take the yellow area, which we define to be a of b, and I'm going to subtract away from it the green area, which we define to be a of a. And you can see that. This is the region that I'm talking about right here. This is the region I'm talking about. The yellow area, subtract from it the green area, and I'm going to end up with this region 1 right there, which is going to be a of b minus a of a. And we know, because of our knowledge about the definite integral, that a of b minus a of a is equal to the definite integral from a to b of f of x dx. We know that. Okie dokie? So we're going to let that guy right there be statement 1. We're going to come back to him. Statement 1. The integral from a to b of f of x dx is equal to a of b minus a of a. That is statement 1. And then we're going to look at the same picture in like manner we're going to region 1, but instead of going from a to b, we're going to go from a equals x, some x, they're just arbitrary things, and we're going to go from x and we're going to move over h and end up at x plus h. So we're going to start at h, move over, start at x, move over this h is a distance, and we're going to go to x plus h. And using the same area function, in the same manner as I did before with the yellow minus the green, I have this region 1 as being a of x plus h minus a of x. Pause the DDO and let it soak in. Now that you pause, so region 1 is going to be a of x plus h minus a of x. Is that region 1? Well, you know what I want to do? I want to estimate that region 1. I'm going to estimate that region 1, by golly, with a rectangle. With a great big rectangle right there. What rectangle am I going to use? I'm going to use the rectangle that has base of h and height of f of x. I'm going to look at that rectangle right there. A pretty good estimation. Look at it right there. So region 1 is approximately h times f of x, base times height. Base times height. We've done a lot of base times height when we were developing the definite integral. We did rectangles, and we infinitely many rectangles. But I don't want a big rectangle right there. Base of h, height of f of x. R1 is approximately that. Well, what does R1 equal? Well, we saw in the previous slide I get a little worked up on this, so I apologize. R1 equals a of x plus h minus a of x is equivalent to this rectangle, which is h times f of x. That's very nice. Some of you know where we're going, some of you don't. But that's okay. Look what I'm going to do, and look what I can do. And this is the glory of calculus, the glory of limits. H does not equal 0. If h doesn't equal 0, I'm allowed to divide by it. And I'm taking this approximation statement here, and I'm dividing both sides by h. So a of x plus h minus a of x divided by h is approximately that f of x there. And what do we do in calculus? We don't like big h's. We don't like little h's. We want h infinitely small. And that's exactly what we're going to do. Because if I go back to my graphical representation, and if I take h infinitely small, what's going to happen? Then this region 1 is almost represented by f of x. Where am I? I believe I'm here. Oh, ahead of myself right there. And so I'm going to take the limit as h goes to 0 of this creature right here, is approximately that. And hey, what is this? What is that? What does that look like? You're digging dog daggone right. That, ladies and gentlemen, is a prime of x. So a prime of x is equal to this limit. Well, and if I take h goes to 0, I'm just going to let it equal f of x. And this is going to be statement 2. So a prime of x, the derivative of that area function, the derivative of that accumulation, if you will, of that accumulation function, is little f of x. So we were actually looking at the derivative of the cube. Yes, we were. And we'll talk about that a little bit more. But this is going to be statement 2 for us right here. That a prime of x, by the definition, is a prime. This is equal to a prime by definition. And this is equal to f of x because of the discussion we had with the rectangle on h approaching 0. Hey, what does this statement say? By definition. This statement says, by definition, that that area function, a of x, is an antiderivative of little f of x. That's very interesting, and it's not only very interesting, it's going to be extremely useful. Well, let us let a of x equal f of x, because when we usually talk about the antiderivative of little f of x, we usually talk about capital F of x. Well, let's let this a of x be capital F of x. And recalling statement 1, which was the integral of the definite integral from a to b of little f of x dx is equal to a of b minus a of a, letting capital A of x be capital F of x, the definite integral from a to b of f of x dx is equal to capital F of a, b minus capital F of a, such that capital F is an antiderivative, i.e. the derivative of capital F is little f of x. This, ladies and gentlemen, is the fundamental theorem of calculus part 2. This is the part of the fundamental theorem that we use to evaluate a definite integral. This is the part that calculus students like because they evaluate the definite integral. This is the uninteresting part, if you will. This is the non-elusive part, if you will. Let's continue our discussion. Here comes the sweet part. instead of considering some f of x, let's just consider a horizontal axis that's represented by t, and look at a function y is equal to f of t, where t is the horizontal axis. And what we're going to do is we're going to let x be some t. This x is going to be some t value, where x is going to be greater than a. The only restriction on x is going to be that it is greater than some arbitrary a. So I'm looking at f of t, and we've done that a lot in calculus. I'm certain that you have. X is going to be some t, and what are we going to do with this? What we're going to do is, again, I'm going to look at this region 1 in like manner, the same area function. I'm going to look at a of x minus a of a. I'm going to look at that region the same way that I've been doing since the beginning of my discussion. And I'm going to say, hey, you know what? That is equal to the integral from a to x of f of t dt. And what I'm going to do here, now this x is the guy that was varying. That's the variable in this equation here. This is the variable. Keep that in mind. A is not a variable. A is called an arbitrary constant. What I'm going to do, this is an equation, true, from our previous discussion. I'm going to add this constant. A is a constant. A of that A is also a constant. I'm going to add that to both sides. And now I have a of x is equal to the integral from little a to f of x, f of t dt, plus this a of a. This is an equality. This is an equation. And what I'm going to do here, I'm going to go back to that statement right here. I'm going to, hey, differentiate both sides of that equation. Done that lots? I'm not only going to differentiate both sides of that equation, I'm going to differentiate both sides of that equation with respect to x. So I'm going to d dx a prime of x. I'm going to d dx this sum. And I know because differentiation is a linear operator, if you're not familiar with that term, that simply means that if I'm going to differentiate a sum, it's going to be the derivative of the sum is the derivative of the pieces of the sum. Well, what's the derivative with respect to x of a of x? A prime of x. And now I'm going to differentiate this piece and differentiate this piece. Well, this is a constant, and the derivative of a constant is 0. So we need not worry about that piece, but I'm going to tell you, for those of you taking the AP calculus test, as you will, this statement here comes up time and time and time again on those accumulation functions, which I will touch on just briefly at the end of this discussion. And then we will have more videos on those problems to follow. But I'm differentiating this piece, which is a prime. I still haven't differentiated this piece. The derivative of this piece is 0. So here, I'm worried about this state. Whoa, wait a minute. Slow, whoa. Hey, recall from statement 2. What does a prime equal? Go back in your notes, rewind the video. I wonder if I can get to statement 2. See, I'm here. Oh, maybe I can get there. Well, I'm not quite sure where statement 2 was. Well, I'm going to go back here. You rewind it yourself, ladies and gentlemen. But hey, from statement 2, a prime of x is equal to f of x. If a prime is equal to f of x, and if a prime is equal to this statement right here, by the transitive property, f of x must be equal to the derivative of this with respect to x, and it certainly does. The derivative with respect to x of this integral from a constant to x of f of t dt is equal to f of x. This is the fundamental theorem of calculus part 1. This is the part that's elusive for many calculus students. This is the important part. This is the sweet part. Where does that come up? On your AP calculus test, on your AP assessment. Here's where it comes up time and time again. They will ask you, they will give you some function of t. And they will define some accumulation function. Now this is not necessarily an area function because if you notice, f of t goes below the x-axis. So it's going to be called one of those net change functions, one of those accumulation functions. But nevertheless, you will see many problems. And this particular accumulation function is going to start from -1 and go from x, where x is some value on the t-axis. And it's going to be defined to be from -1 to x f of t dt. What do you need to know? You need to know that a prime is equal to f of x. Fundamental theorem of calculus part 1. So when you see these problems, what you are actually looking at, if you see an accumulation or net change function defined, you are going to be looking at the derivative. This is the application that you will be assessed on over the fundamental theorem of calculus part 1. So, not many examples, and I apologize. I will follow with a video on a couple nice examples that uses this fact here, and that uses this culminating fact of fundamental theorem of calculus part 1 here. But it's good to know where this comes from. Nice layman discussion about that. Catch you later.